There is this deeply frustrating paradox in software architecture, and honestly, just in system design across the board.
Oh, absolutely. It's everywhere.
Right, like you make this conscious decision to make your system rigorously safe.
Yeah.
You want to handle every edge case, catch every potential failure, make sure nothing slips through.
Yeah, you force the system to verify every single branching path.
Exactly.
Hmm.
But in doing so, you inadvertently make the system entirely unreadable for the actual human beings who have to maintain it.
You swap out unpredictable behavior for, explicit, rigorous safety checks.
Yeah, and suddenly you are staring at this wall of logic that demands like a PhD in mental gymnastics just to trace a single operational path.
It's the eternal tug of war between mathematical correctness and human cognitive capacity. I mean, the machine is perfectly happy, right?
Right, the compiler loves it.
Exactly. The compiler loves it. But the physical structure of that safety forces the human reader to visually parse all those branches simultaneously. The human brain is just completely overloaded.
Which brings us to today. Welcome to today's deep dive. We are jumping into this brilliant piece of technical writing that tackles this exact architectural dilemma head-on.
It's a really fascinating read.
It really is. We are looking at a developer's journal entry by an author named Ang. It's titled Notes on Haskell Programming, Part 156, and this was published on June 8th, 2026.
A very specific, very deep entry.
Yes, and I want to set the stage for you listening right now. While the source material is deeply rooted in the mechanics of Haskell, the underlying conflict is a masterclass in the philosophy of maintainability.
Oh, for sure. It applies to any language, really.
It does. We're looking at how a system communicates its intent to the next person who opens the file.
And that is the perfect lens for this piece, because Ang is not just, solving a localized bug here.
Right.
Ang is navigating that tension between writing code that perfectly executes a task and writing code that clearly explains its own narrative to the developer.
Okay, let's unpack this.
Yeah.
Because Ang's starting point is a trap most developers are intimately familiar with.
Oh, the classic refactoring trap.
Yes. So Ang is transitioning away from a function called decode UDFF8. Now, the issue with this original function isn't that it fails to decode text under normal circumstances.
No, it works fine when the data is perfect.
Right. The issue is that it is fundamentally reckless. When it encounters malformed data, it does not politely report an error.
It just panics.
Exactly. It simply throws an exception and crashes the entire process.
It is basically a landmine. I mean, the function signature itself is essentially lying to the developer.
Lying how?
Well, it claims it will take a sequence of bytes and reliably hand back a string of text. But it completely omits the fact that it might just blow up the execution thread instead.
Right. A minor detail.
Yeah, just a small oversight. So Ang does the responsible architectural thing here. Ang swaps out that dangerous function for its explicitly safer counterpart, which is decode UDFF prime.
The prime version.
Yeah.
And the crucial difference here is that the prime version returns in either type, right? It forces the developer to handle both the success state and the failure state as, like, first-class citizens in the logic.
Precisely. Instead of throwing this invisible exception into the ether, it returns a strict contract.
Right.
It tells the compiler, you must deal with the universe where this failed and the universe where this succeeded.
But here is the architectural consequence of that. By forcing the explicit handling of every something, either result, the code immediately devolves into a series of nested case statements.
The dreaded wedge of doom.
Exactly. Instead of reading straight down the page, the logic marches diagonally across the screen.
Yeah, you check if step 1 succeeded.
Right. And inside that success block, you attempt step 2 and check if that succeeded.
And inside that block, you attempt step 3. It just keeps indenting.
It completely destroys the linear readability of the file. And I want to pause on this because it reminds me of car safety features.
Oh, I like this. How so?
Well, imagine you switch from a car that just randomly breaks down without warning, that's the old function, to a super safe car with a dashboard full of warning lights.
Okay, sounds good so far.
Right. But now the warning lights are so bright and so blinding that you literally can't see the road through the windshield.
That is a perfect analogy.
So, if making code safer makes it harder to read, aren't we just trading one hazard for another? I mean, if I can't read the code without losing my place, I'm highly likely to introduce a logic bug simply because I misread the indentation level.
This raises an important question about how we define safe systems in the real world. Because the physical layout of the code directly dictates the cognitive load required to hold it in your short-term memory.
Right. It's not just text, it's a mental map.
Exactly. When you are forced to read deeply nested case statements, you are maintaining a mental stack.
Which is exhausting.
It is. You might be reading the execution logic on, say, level 4 of the nesting, but you simultaneously have to remember the specific error condition that was established way back on level 1.
And human beings are famously terrible at maintaining a mental stack. We drop that context almost immediately.
We drop it, we misinterpret it, or we simply gloss over it. A dense wall of explicit safety checks creates this camouflage effect.
Camouflage, like hiding bugs.
Exactly. A subtle, critical bug can hide in plain sight because the developer reviewing the code is just too exhausted by the boilerplate to notice the logic flaw.
Unreadable safe code is often just a delayed catastrophic failure.
Perfectly said.
So Aang is staring at this diagonal wedge of doom, knowing it is mathematically sound but structurally unsustainable. And this is where the journal entry pivots.
Yeah, Aang finds a way out.
Aang deploys a remarkably elegant alternative. They manage to flatten that entire nested structure back into a straight line.
By utilizing the bind operator combined with the where clause.
Right. The resulting core logic is reduced to something incredibly stark. It's literally just decode to text, bind, run, parser prime.
It's beautiful. Let's look at the behavioral mechanics of that bind operator, though, because it is the engine driving this entire solution.
Yeah, break that down for us.
The bind operator is essentially a context-aware connector. It is built to natively understand that either type that we just discussed.
So without getting bogged down in how the operator is physically typed on a keyboard, functionally, it's taking the output from the left side, the decoding attempt, right?
Right.
And it's making a strictly controlled decision about whether to feed it into the right side, which is the parsing function.
That is the core mechanism. If decode to text evaluates to a success, the bind operator automatically unpacks that successful text and passes it directly as an argument into run parser prime.
Okay, but what if it fails?
If decode to text results in a failure, the bind operator intercepts it. It bypasses run parser prime entirely.
Oh, wow.
Yeah, it simply propagates that error down the chain to the end of the execution block.
Let me map this to a physical analogy, because the concept of automatic short-circuiting is really profound when you think about cognitive offloading.
Go for it.
Imagine a highly coordinated relay race. In a badly architected race, the nested one runner trips and drops the baton.
Okay.
But runner 2 is programmed strictly to grab whatever's in front of them, sprint the next leg, and hand it off. So runner 2 scoops up a handful of dirt, sprints down the track, and hands dirt to runner 3.
Which is terrible.
Right. By the time they cross the finish line, the judges have to reverse engineer why they are holding dirt instead of a baton.
That is a very accurate depiction of cascading errors in imperative systems. You spend hours tracing the dirt back to the specific runner who tripped.
Exactly. But the bind operator completely alters the mechanics of the race. It acts as an active referee running alongside the track.
I like that, the referee.
Yeah. Runner 1 attempts to decode the text. If they succeed, the referee facilitates the handoff to runner 2. But if runner 1 trips, if that either type returns an error, the referee instantly blows the whistle.
The clock stops.
The clock stops. Runner 2 never even leaves the starting block. The referee simply walks the dropped baton straight to the finish line and logs the exact failure.
The brilliance of that architecture is what it allows runner 2 to assume.
Right. Runner 2 can just relax.
Completely. The function signature of run parser prime doesn't need to contain any defensive logic to check if it was handed a handful of dirt.
Because it knows it wasn't.
Exactly. It is mathematically guaranteed by the referee, the bind operator, that if it is invoked at all, it possesses a valid baton.
Which explains why Aang could reduce the main code down to just lining up the runners. Decode to text binds to run parser prime.
Yes.
And Aang specifically highlights the use of a prime helper function here, run parser prime, which is isolated down in a where clause.
That where clause acts as the perfect organizational counterpart to the bind chain.
How so?
Well, by pulling the intricate mechanics of run parser prime out of the main pipeline and defining them at the bottom of the file, Aang separates the what from the how.
Oh, I see.
The main pipeline at the top reads as a clear, high-level narrative. Decode the text, then parse it.
Nice and clean.
Yeah. And the where clause serves as an appendix that the compiler can reference without forcing the human reader to wade through the micrologic, unless they specifically need to debug the parser.
That is so clean. And Aang then uses this moment of elegant resolution to draw a cross-language comparison that is really illuminating.
Especially looking at how Elixir handles pipelines.
Yes. Aang compares Haskell's bind operator to Elixir's pipe operator.
On a purely superficial level, they appear to serve the exact same function.
Right, they both look like arrows pointing right.
Yeah, both operators allow a developer to chain operations sequentially from left to right, feeding the output of one function into the input of the next, avoiding all that deep nesting.
But conceptually, they operate in completely different paradigms.
They do. Elixir's pipe is strictly a mechanism of data flow. It is entirely agnostic to context.
Meaning it doesn't care if there's an error.
Exactly. It simply takes the raw return value of function A and forces it into function B as the first argument.
Regardless of what that return value actually represents.
Right.
Like if function A returns an error tuple, Elixir's pipe will just shove that error tuple directly into function B. And if function B is not defensively coded to handle an unexpected error tuple, the entire pipeline violently crashes.
Exactly. The Elixir pipe is the naive relay race. It just hands off whatever is there, even the dirt.
Right.
The Haskell bind operator, as we established, is deeply context-aware.
So what does this all mean? If I am architecting a system in Haskell, and I explicitly do not want the context-aware short-circuiting of the bind operator.
You don't want the dirt to pass.
Yeah. Say I am working with guaranteed data, or I am intentionally deferring error handling, and I just want a lazy, dumb pipe to pass data from left to right. Does Haskell force me to use the bind referee?
It does not. Ang points out that if you want the exact semantic equivalent of Elixir's dumb pipe in Haskell, you reach for the reverse application operator.
Oh, interesting.
Yeah, it's from the data function module. It performs the exact same agnostic data pass-through as Elixir.
Okay, so Haskell provides both the intelligent referee and the blind pass-through.
If we connect this to the bigger picture, the distinction between those two operators illustrates the fundamental difference between control flow and data flow.
Break that down a bit more.
Well, the bind operator is an instrument of control flow. It is actively making structural decisions about whether the next function should execute based on the contextual state of the system.
Okay, makes sense.
The reverse application operator is an instrument of data flow. It solely dictates what data is routed to the next function, abdicating all execution decisions.
That is a phenomenal distinction. You select your operator based on the specific narrative your architecture requires.
Exactly.
Are we carefully navigating a conditional minefield, or are we simply routing telemetry data down a chute?
That's the choice. And that concept of selecting the right architectural narrative leads us directly to the alternate solution that Ang evaluated and ultimately rejected.
Yes, I want to spend some serious time on this rejected alternative, because it exposes a completely different philosophy regarding abstraction and readability.
It really is a totally different mindset.
So someone suggested to Ang an alternate path to avoid the nested case statements.
Yeah.
This path involved using a do block combined with explicit value unpacking, using that little left-pointing arrow, and heavily leveraging a module called data bit functor,
Yes.
specifically utilizing a function within it called first.
It is a very common, highly academic approach to functional refactoring.
But here's where it gets really interesting, because conceptually, a do block is widely considered the holy grail of readability in functional programming, isn't it?
That's the reputation it has, yeah.
Its entire purpose is to take complex, abstract monadic chains and make them look like standard imperative top-to-bottom execution steps.
Right. Execute step 1, bind the result to a variable, execute step 2.
Exactly. It reads like a recipe.
Yeah.
So why would Ang vehemently reject a paradigm specifically designed to mimic natural reading?
To understand why Ang rejected it, we have to break down what data bit functor is actively doing to the structure of that so-called recipe. A bit functor is, at its core, a mathematical interface designed for structures that inherently possess two distinct type parameters.
Like our either type.
Exactly. Our either type is a perfect example. It has a left side explicitly reserved for errors and a right side explicitly reserved for successful data.
Okay, so it operates on a bifurcated structure.
Yes. And the first function from that bit functor module is an incredibly precise tool.
I'll just do.
It allows you to reach into that either structure and apply a transformation exclusively to the first type parameter, the left side, the error state.
Oh, wow.
Yeah, while mathematically guaranteeing that the right side, the success state, remains completely untouched.
I see. So if my original decode EF8 prime function throws a very generic, unhelpful error, I can use the first function to reach in, grab that generic error, and wrap it in a highly specific custom domain error for my application.
Right.
And I can do that without having to worry about accidentally corrupting the decoded text if the operation was actually successful.
Mechanically, it is pristine. It is mathematically elegant. But let's look at the fallout of applying that mathematical elegance to the physical code you were trying to read.
The actual text on the screen.
Yes. Inside this proposed do block, the developer is not just listing the steps of the recipe. On a single line of code, the reader encounters the unpacking arrow, an invocation of the first function, the specific formatting logic required to map the error state, and then finally, the actual core decoding function.
Oh my. So instead of a clean narrative step that says decode the text, the line now physically reads. Attempt to decode the text, and simultaneously, if this fails, here is the intricate inline transformation required to morph the generic error into a domain error. Now please unpack the ultimate result.
Exactly. And then you move to the very next line in the do block, and you encounter the exact same interwoven complexity for the parser step.
It forces you to process the error mapping logic explicitly at every single step. It's completely entangled with the actual business logic.
Yeah, what's fascinating here is that Eng's critique is not about the validity of the math.
Right.
Eng's critique is entirely about the cognitive load of explicit abstraction. Eng states this approach requires the reader to mentally decrypt the file.
Mentally decrypt.
Yes, calling the resulting code an alphabet soup.
That makes perfect sense now. With the bind operator approach, the error handling wiring was elegantly hidden behind the drywall.
I like that.
The do block, combined with inline bit functors, rips all that wiring out, dumps it in the middle of the living room floor, and forces the reader to step over it on every single line.
It is the architectural equivalent of reading a novel where every single sentence contains an inline parenthetical citation detailing the Latin etymology of the verb that was just used.
That sounds miserable.
The information is highly accurate, it is technically rigorous, but it completely destroys the pacing and the narrative flow of the story.
You lose the plot entirely. You are so busy verifying the error transformations that you forget what the function is actually trying to accomplish in the first place.
Eng is making a definitive architectural stance here. If a code base requires mental decryption just to read top to bottom, it represents a failure of communication.
Regardless of how clever the math is.
Regardless of how mathematically sophisticated the underlying abstractions might be, you haven't actually reduced the cognitive load from the original nested case statements.
You just changed the flavor of the confusion.
Exactly.
So, to synthesize this entire journey for you listening, we started with a fundamental architectural requirement.
Yeah.
The need for explicit safety.
Right.
We upgraded to an either type to catch errors, but immediately fell into the wedge of doom, trading invisible runtime crashes for unreadable, nested structural clutter.
We hit that wall of cognitive overload.
But then we found true structural elegance. We bypassed the naive data pipes and utilized the bind operator, our intelligent referee, allowing for automatic short-circuiting.
Yeah.
We flattened the execution path and sequestered the micrologic into a where clause, achieving both rigorous mathematical safety and pristine linear readability.
We solved the paradox by offloading the routing logic to the operator itself.
And crucially, we learned a vital lesson by analyzing the path Eng actively rejected. We saw that attempting to force monadic logic into an imperative do block and over-engineering the error handling with inline bit functors actually destroyed the readability it was supposed to provide.
Absolutely.
We learned that the most mathematically clever solution is frequently the most hostile solution for the human being who inherits the code base.
It is a reminder that you are not just writing instructions for a machine. You are writing documentation for your future self.
Which is the core takeaway, really. Whether you are architecting a back-end system in Haskell, drafting a multi-phase project proposal, or writing a complex legal contract,
Right.
the ultimate goal of structure is comprehension. The tools we choose should exist solely to reduce the cognitive load of the reader, not to showcase the author's mastery of obscure grammar.
If the structure obscures the intent, the structure has failed.
I want to leave you with a final thought to mull over, building on Eng's conclusion. If an experienced developer writing their 156th technical journal entry on Haskell looks at a do block interwoven with bit functors and immediately dismisses it as an alphabet soup requiring mental decryption,
Yeah.
it begs a massive, somewhat uncomfortable question about our industry. Is readability actually an objective, measurable standard? Or is it entirely subjective, based purely on the specific abstractions a developer happens to be comfortable with?
That is the dangerous frontier of senior architecture.
It really is. At what point does our pursuit of elegant, mathematically pure minimalism mastering tools, like a Bond operator and advanced type classes, cross an invisible line?
When does it become too much?
Yet,
Exactly. When does our clean code mutate into an exclusionary dialect that makes the system completely inaccessible to a junior developer who is just trying to learn how the application works? We demand safety from our systems, but if the dashboard is so cryptic that only the lead architect knows how to read the warning lights, we haven't really made anything safer at all. We have just locked everyone else out of the car.